In this video, we are going to talk about differential pairs, and we are going to have a look at a couple of examples, and then also we will talk about what is important in differential pairs, and also how you may want to maybe simulate them if you would like to do that. Is that what we are going to talk about, Saish?
Yes, indeed. Yeah, I'm excited to talk about this.
Okay, so I think this is one of the very interesting examples which you prepared for this video, and it's about like routing differential pair and then having crosstalk with different track, and there is difference like if you have N signal routed close to this aggressor or P signal.
Yeah, so I have this example where I'm showing an aggressor is a single-ended net. So many a times when we implement this routings, we sometimes have some differential signals next to an single-ended signal. So here I have an example where you have a differential pair and an aggressor with a spacing of one S. The other one was 2 times this spacing, and the third case is 3 times the spacing. Okay, and
S
in
is the
this.
space between the differential pairs. Okay.
Yes, indeed. Yes, yeah. And what I have here in the left is I'm showing the ports. This one is an input side, the other one is an output side. So we have a lump port directly. I can show you a few slides others on how we can de-embed things and all, but this is the most simplest way to do the setup and do it quickly, okay, to get some more insights. So you have this, what I've done is done an EM extraction of this data. So since there are 3 ports on one side, the other 3 on the other, you have this 6-port file, okay. On 2 of the ports, we have connected balun and converting that to a differential signal. And whereas the single-ended net is our aggressor. So aggressor, we are putting in, like we are feeding in the signal, okay, and we are viewing the signal as near end differential crosstalk and near far end differential crosstalk. Okay, so when the signal get
I will interrupt you. I will interrupt you. So when we have a look on this schematic, I just would like to be sure everyone understands what we see. So the biggest part in the middle, that's our PCB layout, correct?
Yes, that's the EM extracted S parameter data. Yes, that's the PCB.
So basically, when someone would like to do simulations of their board, one of the ways how this is done, when they finish layout, they create this S parameter file of the PCB, and then they can connect there this kind of like signals, and they can see how the results will look when these signals will flow through their custom PCB.
Yes, correct, indeed.
Okay.
So to this channel can be represented in 3 ways: a pre-layout models, which are lump models or a transmission line; a post-layout model, like you have already implemented the layout and you are getting an S parameter data out of it; or third thing is you have a fabricated board and you are actually doing the measurement and getting that S parameter data. So
so basically you can create the S parameter model also just by measurement.
Yeah, by measurement as well. So this could be even a measured data that you will plug in, and then you will have you will see what is the impact of a single-ended aggressor net onto a differential pair. Okay, so
again, I will interrupt you. Sorry. So on the left and on the right, these are the blocks which are changing single-ended signal to differential pair signal.
Yes. Yes, yeah, it's called balun, and you see that there is D and C. Also, D is a differential and C is a common signaling mechanism. And on the other side of the block, you see plus and minus, basically. So that converts the differential signaling and common signaling, basically.
Okay, and this basically makes the simulation easier
yes,
for
much
differential
simpler.
pairs.
Yeah, much simpler. You can remove this as well, but then you will have to type your equations and all of that. Okay, relatively. So this becomes relatively simpler. Okay.
And what is the so the source of the aggressor? What is the aggressor doing?
Yeah. So aggressor is so when let's look at this example of three lines. So the bottom two lines are your nets, the P line and the N line, and then your aggressor is the signal is getting launched. So your victim line is usually the quiet signal. So there is no signal flowing on that net. So you will see that we don't have any source connected to your differential channel from either side. It's just a resistor. So when you launch a signal starts traveling. Okay, now I'm Eric's student, so I'll be the signal. Okay, so once we be the signal, the signal starts walking through that trace, and there will be a crosstalk happening. So the fields will interact with the adjacent net, and some energy will get transmitted to the adjacent net. And once it let's say we are in the middle of this, the signal, there is a crosstalk happening. So that signal on that differential pair, it will also go both direction. It will go in the forward direction and it will go in the backward direction. So when it goes in the forward direction, the signal that we see on the other side, we call that as far end crosstalk. But now since this crosstalk is on a differential pair, I'm calling it as FEXT underscore diff. So this is differential signal far end crosstalk. Whereas on the near end side, we will see the near end crosstalk, NEXT, that which is differential. So that's what we are seeing on the differential D port of this schematic, basically, because we are interested in differential signaling mechanism.
Okay.
Okay.
Okay. In this graph where you just have your cursor, so this is the signal on the input and signal on the output.
Output.
So we can see it's rising from 0 to 1 volt, and a little bit later, after 0.6 nanosecond, it will arrive at the end.
Yes. So you see what I have done here is you have a label here, and on this net I have V underscore in. So that is V underscore in. So this is when the signal is getting launched on this PCB. Okay. And on the other side of the PCB we have V out. So V out is the blue curve, and that's when it is out. Okay. So this is the input, this is the output. So it takes 0.6 nanoseconds for the signal to go from port, the left port to the right port. Okay. And like other thing that it's strongly ingrained now on like, if you have repeatedly watched Eric's videos, is the signature of your far end crosstalk and near end crosstalk. Okay. So your far end crosstalk,
okay, I will interrupt you. So this this second graph, this is basically the signal which is on the neighbor track of the aggressor.
Yes. The middle one. This is the victim. So victim is our differential pair. Okay. So signal has got coupled and there is a crosstalk.
Oh, okay. So basically you can do simulation for the whole differential pair.
Yes. Okay. Yes. So this is for that differential. So we are capturing the signal on this differential pair. And when the signal reaches the other end, that's when you see the signature of your far end crosstalk. So you see far end crosstalk at 0.6 nanoseconds. So that's when all the signal gets accumulated at the far end side. Okay. Whereas the near end crosstalk, the signal goes all the way and then comes back. So it usually has a round trip time. Okay. So its length is usually twice. So you will see that it's positive and it's 1.2 nanoseconds long, kind of thing. So you also see the same feature or the same signature of the crosstalk, basically. Okay. So this is what we see out here. Okay. And then we have the thing in this schematic we have is three spacings we have used. So one is just one spacing, which is like for a differential pair we have a width and then we have a spacing. So that is that if we retain that same spacing S, let's say, then we are like three signal tracks next to each other.
Okay. I'm curious. Because this is very important, because when someone is doing PCB layout, they would like to know how far from differential pair they need to route. So let's have a look.
Yeah, so here we have these three cases, one spacing, two spacing, and three spacing. Okay, and the responses that we have seen in the previous graph, I have now separated them. So all the three near and crosstalk are listed down here. Red is one spacing, the blue is the two spacing, and the pink is the three spacing. And you clearly see that as the separation increases, you clearly see that there is a reduction in this near end crosstalk, as well as in the far end crosstalk. You see that the one spacing, it's 158.2 millivolts, but then from 2 spacing and 3 spacing, it's relatively the same, right? So it's not having any major impact. So you need to ensure that it's 2 times or more, basically, of the spacing. And also other thing is, what is the worst case scenario? If you, the worst thing is you would put it one spacing separation, right? So that's why I have listed down, hey, one spacing, what is the percentage of near end crosstalk and percentage of far end crosstalk? So this percentage of near end crosstalk is 9%. And how we come to this 9% is we divide this 88.80, okay, divided by 1 volt, and that's what we get, 9%. And similarly, for 158.2 millivolts divided by 1 volt, we get 16%. So this is the maximum limit of crosstalk that we are introducing towards near end and far end, basically.
It's quite a lot, actually. I'm very surprised. Even for like 3 times spacing, it's still quite a lot.
Yeah, yeah, yeah. And so to extend on this, I have another case, okay, and this is something that I have never thought of, and it just out of a discussion with a friend, this thing came up. Okay, so we were curious that, hey, we have we just saw the signature of this aggressor single-ended net and on a differential pair. So your red is that aggressor, okay, that's the culprit, and you see a P and an N, like the calm, quiet lines, okay, the blue lines out here. And what happens if the polarity of these nets are changed? So differential signaling, you see that one is going to high and the other one is at low, and they just swing together, right? So here in this sense, the very first case, we see the signature as expected. So when the signal reaches the other end, we see the far end crosstalk negative. Okay, that's fixed. The pink one is the next. Okay, when we see that it's positive and its length is 2 times the length, basically. So this is as expected. But when we change the polarity, we see that the far end crosstalk is now positive. Okay, and the blue, and sorry, the pink curve here is the near end crosstalk, and even that's inverted. So this was like, hey, that means that the polarity does have an impact. So we were like, but we need to understand what's happening here, or how to build intuition further on this. Okay, so to leverage our previous understanding, a differential signaling is always complementary, right? The signaling is happening complementary. So for a moment, let's ignore the net n and just focus on net p. Okay, so whatever signal that we see on net p, that is getting impacted, and accordingly the signal on n is also getting impacted, but just complementary. So let's say if P is held high, okay, that's positive. That's why it's held high. So it is just like a single-ended net. Okay. So when an aggressor signal, there is a signal on an aggressor net and it's getting coupled, you will see a same signature as if there are two single-ended nets and the crosstalk is happening. So we see the same signature as expected. But now when we have the other case where your aggressor is next to a negative line, the signal is on P, like the high P is held high. So N is the negative, it's held low. So whatever signature we would have anticipated, we will get inverse of it.
Yeah,
So
I
your
understand.
your your far end crosstalk is now positive, and your near end crosstalk is negative.
But
But
values are basically same. They are,
same values are same.
yeah.
Values are same. Okay. It's just because of why the N is held low and P is held high. That's because how this signaling mechanism is operating for a differential pair.
So basically, when routing a single-ended signal close to differential pair, basically you will get kind of same amount of crosstalk, just
Yes.
opposite. Okay, what
Yeah.
about the differential pair and differential pair?
Yeah. So that's also something that we have done, and that's where was the very next thing, uh, and it is so interesting, the results that we got out here, that I'm like, okay, I'm done with the simulation, but I have requested my friend that maybe in over next couple of weeks we should build a board together and then do some measurements out there. Okay, so we have this example. Now here we have four nets. Okay, like four single nets. You'll see that they're forming two differential pairs, the first one and the second one, and the plan is same. we have one spacing, the two spacing, and the three spacing. So you clearly see that the two differential pairs are getting separated.
Okay, I'm
Okay.
curious. What is the result?
Now, it, yeah, so this schematic is again the same. So you have an S parameter block with these two balance. Okay. This is a response. Okay. So you see, this is positive. This is, at least in our first case, we saw that we were getting a correct response, but here we are always getting a negative, a different response. So I'm like, why? And does this sequence matter? So that was another next question, because when an aggressor was next to P or an aggressor was next to an N, a single-ended one, the response flipped. So that became our immediate next question. Okay, so that's what we did. We have three cases here now. So one is a positive net and a negative net, followed by a positive and negative. So this is the standard routing, and we see this signature. So the near and crosstalk is inverted, like the negative, the far and crosstalk is positive. Okay, the red curve is the input, the blue curve
So
is
they
out.
are all the same.
Yes, that's the finding. So I'm like, this is what it is. So I believe that's where this gets tied up to the benefit of a differential pair, that hey, it is immune to noise. Like if you have differential to differential, they're not impacting each other, and you clearly see the values also, right? They were like 9% and 15% line. Now it's like 5.8%,
Yeah,
4%.
this
So
looks
that
much
was,
lower.
yeah, and then that's the benefit of using a piece using a differential signaling for for your critical systems, basically. Yeah,
So
this is
basically, what
immunity to the
this
noise.
means that when we are routing single-ended signal close to differential pairs, we need to be more careful with spacing. Uh, as and when we are routing, for example, differential pairs close to each other, then there is not going to be as much crosstalk as
Yes.
in the thing. And
Yeah.
it really doesn't matter if it's PN or PN.
Yeah.
It's all the
Yeah.
same.
Yeah. And then the other thing is, folks who have done the routing, and you also can speak from your experiences, routing a differential pair is already an headache relatively. Okay. Because the way it is coming out from the pin and the way it is going out, the pins are already fixed. You need to ensure that it goes accordingly. You need to do a length matching and all of that. So now you don't have to have another headache that I need a P and N and then again a P and N. If the pins are based such that you can be little free, but you ensure that it's just a pair. You are
Mm-hmm.
setting those pairs together, and then this any sequence would not matter,
Mm-hmm.
basically.
This is
Yeah.
for S3 spacing or
No, this is for S1. So this is the
S1?
tight.
Ah, okay,
This is
this
the
is the
tight
worst
one.
one. Okay.
This is the worst one. So if you separate it further, it's going to reduce. So I was like, hey, let me not create another extra data set like that. That point was already covered in our previous example. So this was a new highlight. So I just left it here on this,
So this is
basically.
and the previous one with the aggressor only was for S1 too. 20, yeah, page 20. Yeah,
Yeah. Yeah. So this is also the worst case that I have shown.
S1.
So
Okay.
yeah. So when you change, the signatures will remain the same. It's just the amplitudes will reduce, basically.
Okay.
The values will reduce. So they will have the same responses. It's just they will be flipped one.
Mm-hmm.
If you change these combinations,
Mm-hmm. Yeah, I only asked
basically.
because it doesn't say on the slide which spacing this
Yeah, so I
result.
have it here in the name V
Oh yeah,
out
I
for
see. I see.
S1
Oh, okay, I didn't notice.
separation.
You are
So
right.
that's one. No, once you have once you're a Eric student, you'll have to like ensure that all your data is out there explicitly. Yeah.
Okay. So what will happen if we have to do length matching, or if we don't do the length matching correctly between the phases?
Okay. Yeah, so I have an example out there. Let me try to find it. Oh, okay, yeah, this one. Okay, so this is mismatched P and N net. Okay, so here we have four different cases. So there is no mismatch. You have a nice clean differential pair. Okay, then I was like just having fun. You have a long mismatch. You have a medium mismatch, and you have a short mismatch. Okay, so like when you're doing this, like, hey, we're talking about differential pairs, so we really get biased towards viewing TDR response, and we want to ensure that what is our impedance profile, right? Okay, so that's what the very first thing that any typical user will do. They will do an EM extraction and plot this response, and they will see the red curve is the length matched. Okay, so you'll see that there is a port here and there is a port on other end, and then it's going open. Okay, it's going to an open. So it's a clean, flat 87 ohm kind of a resistor. But then if you see a long section, this is a blue curve. So it starts at 87, it goes all the way up to 115, then comes back, again goes up. So this meandering section. And when we have this meandering section, there are also signals that would be jumping ahead. There will be some crosstalk and all of that. So the impedance profile is not 87 constant out there. Okay. If we reduce that extra, the number of meanders, okay, we see pink response. We just have two discontinuities, larger discontinuities. And when you have this one section, you see that it's flat up for up to 1 nanosecond. You then see just this one peak, okay, going up to 115 and then coming back again. And then you see this, okay. So this one question that typically one should question is whether we will get an eye open or close. If we say that if you don't go there and we directly plug it in this, we'll see a response something like this. Okay, this clearly says, so this is for the mismatched long condition. Okay, so this one is the worst case, and you'll see that there is no eye, and this is at the RX output. So it is at the output of that receiver.
So
Okay.
basically, just this impedance mismatch can kind of close the eye. And it's not
Yes.
even about like traveling the edges together or something like this. This is just the impedance mismatch influence.
Yes, and this is one way of seeing this impedance profile. Okay, but I want to caution that, okay, let's not just put the entire blame on, hey, this is impedance mismatch was the culprit. Okay, uh, because like when we see this TDR profile, I have put this extra information. So again, this one is again from Eric's book. Okay, this is the general criteria to describe the spatial resolution of your TDR. Okay, so there is this relation that you need to have a rise time. Okay, rise time is equal to 0.35 divided by bandwidth. Bandwidth is in gigahertz, rise time is in nanoseconds. Okay, so when you are doing this measurements in your lab or when you are doing this EM analysis, you need to put your F max frequency up to a certain point such that you have enough fast edge to capture the data. Okay, so now here in Eric's book, we have these three examples. Okay, there is an impedance, a flat impedance, let's say of this 50 ohms, then you see it's going all the way up to maybe 60 and then coming back, and then again going to 60 and then coming back, and it's constant. So this is a typical thing. But if you have even faster rate, we would see this peak to be much narrower and much clearer. Okay, but as you see this rise time, it's getting slower. Okay, you don't have enough rise time, you will see that it's getting smeared out. So you're not able to resolve whether this is inductive or not. Okay, so if you look at this graph, okay, let's say we don't have access to this data. If you just see this, what you would feel like, hey, I have a 50 ohm section, then I have a small section which is 61 ohm, and then I again have a 50 ohm section.
But it's not
So
true. There are two places with six.
yes, so this data gets smeared out. So you just cannot only just think it from one domain. Okay, the just, okay, I've plotted TDR. Okay, so it's also like from where you start becoming a SI engineer, you get you create a bias. Okay, people who have a digital design experience from early from their career, or someone who comes from a PCB design environment, they think more in time domain. So the very first thing that they will go towards is TDR responses, okay, and see for an impedance profile. But if someone who's from an RF domain, they will not see this. What they will go is they'll go to this. Okay, they will first plot S parameters and they'll think in frequency domain. So this is where I want to talk about mode conversion. Okay, so for all of these three cases, the mode conversion happens. Okay, so mode conversion occurs in differential pair if there is any asymmetry between the two lines that make up. So the three different cases we see this asymmetry, and this could be a length difference, a loss difference, or even an impedance profile difference.
So I
So
would like
it
to I
could
would
be
like to
three.
point out mode conversion. What we are talking about. This is basically happening when the edges are not traveling together. So when they are
Yes,
traveling together, that should be the differential mode. But
signaling. Yes.
suddenly, if the edges are moved in this space, the common uh, mode is happening. Correct?
Yes. Yeah. So again, this common signaling, differential signaling. Okay, there is nothing common mode, differential mode.
Okay.
I'll later take you to one slide. Like you interact a lot with Eric, so I am certain you will do another video with him. And when you use these terminologies, he'll again be pointing it out to you. Like we have learned it hard way, so I'll go back to one slide. So there is common signaling, differential signaling. Okay, yeah, there is uh, like so that the keep that stressed out. So what here happening is the mode convergence, which is energy is getting converted. Okay, so uh, let's explain this. Let's pick up these first two cases: no mismatch and mismatch with a long section. Okay, so no mismatch, the signal is traveling together. Ideally, because of losses, there should be some monotonic uh, decay in the transmission. So we see SDD21. So a quick input for folks who don't know. The DD means differential in, differential out, and 2-1 means input is on port 1 and output is on port 2. Okay, so SDD 2-1, and we see that its response is good. Okay, it's decaying now. But then if we look at the long transmission line section, SDD1, we will see that there is this uh, like energy loss is happening. Okay, this energy is not going through, but there's energy is leaking out uh, at different places. This energy leaking out, where it is going? Because basically we need to ensure that there is a conservation of energy. Okay, so this energy which got leaked out, it's getting converted. So that's why we call it mode conversion. Okay, basically what's happening is the signal is going into a there is a differential signal that is launched. Okay, and ideally a differential signal, it should not have a common signaling component. Okay, the common signaling should be cancelled out. Basically we are not deliberately inducing it, but because of the profile of this impedance profile of this layout, we are seeing that energy getting converted from differential signaling to common signaling. So that energy conversion, we call this as mode conversion out here. Okay, and now what we see here is SCD21. So port is input is port 1, and that's differential. Okay, and what we are seeing is at port 2 we are seeing the common signaling. So we are seeing at the output end of the other side, we are seeing the common signaling at port 2 with input at port 1, which is differential. And we see that this red curve, ideally, if it's no mismatch, we'll see this response out the blue one, and it's less than -20. So we are not having this mode conversion. That's an ideal situation. Okay. So that's where like I've called it as expected. Okay. But then when you see this red curve, that's of the long thing, the energy is you're seeing the mode conversion, that energy conversion happening a lot higher. And if we just overlay both of these responses, you will see that whatever energy that we lost, you see peak on that same frequencies. So wherever that energy was getting lost from differential signaling, that energy was getting converted and traveling. So that energy is still in that board. It's still traveling, but now it's traveling in the common signaling methodology,
So it's
basically.
basically DC.
Yeah, yeah.
Yeah, and also, okay. So again, I would like to point out a little bit about these graphs. So for everyone who see these like for very first time, uh, up when we are up, when we are 0, that's what we would like to have. When we go down, it means we are losing signal. And when we have a look on the red graph, it means at specific frequency is if our signal needs these specific frequencies, which are very low, like -40 for 1 point something gigahertz, then basically we would not be, our signal would be completely damaged.
No, so this is transmission. So this one is transmission, SDD21.
Yeah,
So yeah, so this is good, but
yeah,
this
but
value should
when
be
we have a
as
look on
low
the
as
red one,
possible.
on the red graph, in the
Yes, yeah,
first.
yes, it is damaged. Yeah, if you put it that way, then yes, yeah, the signaling is not in differential; it's in the common
Yeah,
signaling way. So, and you are not extracting that, the information is not coming out of that. Okay, so the energy got lost, or that information got lost. So you'll not have a good transmission, and that's why you will see this collapsed eye. Okay, that's why your eye got collapsed in the receiver, because for those, sorry, for those frequencies you have a collapsed eye. So
yeah,
you are correct, it's of no use at those frequencies.
yeah. And basically, what also we would like to point out, a signal of specific frequency will contain also different frequencies, not only one, because the falling and rising edge has also
Yes,
different
yes,
frequencies. So, so even if our signal is not exactly at this frequency, which is in this, I don't know, -40 region, we still may get the eye damage, because these damages may be happening on different frequencies.
yes, yes, and that's also again going back to the first thing, the realm of where you are coming from. So most of the RF engineers, they think in single frequency basically, but since this is a digital signal, the square wave is composed of multiple sine waves. So that's where you'll have to think about the entire bandwidth, and that's where previously what we discussed, the rise time is more important than the data rate. Many a times we say, hey, what's your data rate? Is data rate an important figure of merit? In digital, no, it's the rise time. How fast is your rise time, and the fall time determines the quality, the signal integrity challenges that you will get in that agreement.
Okay, so how can we fix this? We should keep the impedance.
Yes, uh, you should route them together. You should, like, these are all the worst case examples that I want to show. So ideally, you need to ensure that you are doing the length matching, and you're routing it correctly, basically. Yeah.
So P and N should be same length, and they should be routed always together.
Yes. Yes.
And if
Ideally.
you have to do this phase matching, then maybe this meander should be very small.
Yes. Very small. Basically. Yeah.
Okay.
So many a times these different standards like USB, PCIe, and Ethernet, and all of them, in their specifications, you will have a margin, okay, of skew that is allowed. So that skew, whatever skew that is allowed based on that. See, if you see, when there was this mismatch between how the signal is traveling, that's when the board conversion was happening. So if there is a difference between that, it will reduce your eye height. Basically, in an ideal case, you'll see a nice open eye, but if you are having some skew, the eye will start collapsing. So based on the different specification standard that you are designing this transmission line for, it will, that standard specification document will give you that, hey, this is the maximum skew that you can allow between the P and the N line. Okay, if you violate that, it will collapse your eye, so eye mask will not get passed. But if you are within that limit, you can do it. And see, these are all very ideal situation examples that I am creating. But if it's a headache, would be an headache to do a routing on an actual board which are multi-layer, you'll have to go through vias and all of that. So in doing so, uh, you the standard specification gives you some benefit as well. You can have tolerance as well,
Hmm.
ideally.
So when you mention vias, basically vias can be also impedance mismatch.
Yes, yes, they are usually the bigger culprits than this routing. Okay, routing, you can usually do small bends and all of that, but VIA is where your reference plane is also changing. Okay, so a good practice usually is someone can do a pre-layout study of what is an ideal VIA, like how they can design some VIAs, how the return VIA should be around it, and all of that. And once that their VIA is optimized, they can replicate that VIA geometries whenever they are making these transitions, basically.
So
Okay.
what did you use to simulate this?
Okay, so to simulate this, we have since, as I said, that the system level simulation requires a lot of constraints and you have to do a lot of analysis. We have a tool called PCI Designer. So all of these nets
We?
that I have
Who's
done.
we?
Oh, so Keysight. So I
Okay.
work for Keysight Technologies. Okay, so yeah, Keysight have got this product called PCI Designer. Okay, so a PCI Designer usually is typically involves a PCI involves a root complex placed on a motherboard, and then you have this client. Like for a client case, you have a card with an endpoint, or if it's a server case, you have a riser card with a retimer, and then you plug in an add-in card. So it has got a lot of these layouts and
Okay,
basically.
so if someone would be interested to have a closer look on this I don't know what is it add-on or it's like completely new software or what is it? I don't know.
Yeah, so this is an add-on feature to ADS. So
Mm-hmm.
ADS is a product that I have used.
Mm-hmm.
So all the simulations that I did and all the setup that I did, I had used ADS for that. And this is another product feature within an ADS
How is
basically.
it
Okay,
called?
it is called PCI Designer.
Mm-hmm.
That's the name of the product
Okay, so I
basically.
will leave a link in description if someone is interested. And I would like to point out, actually, we didn't talk about this equalization, but I created a video, a very good video on this topic. So if someone is interested to understand a little bit more about these very high-speed interfaces like PCI Express, uh, basically there is some kind of uh, how to explain it. There is a lot of things happening after the signal is received by the receiver, by the pins on the receiver. There is a circuit which can actually clear up this signal which is coming, and that's what the equalization is about. And it may be quite complicated, but
It
once
is,
it
yeah,
is done, you can see difference
the
between what is
difference.
arriving and then what is actually detected, like the real signal. It was very good video, so if someone is interested, they can watch it. Okay, so what else you have here in these slides? I'm curious. Did we talk about
Yeah,
all the
so
examples?
no, so I have one more example that I have, and this one was initially I wanted to bring the audience attention to IEEE standard 370. Okay, so this standard recommends the practices to ensure that the data that you have, okay, is of good quality. Okay, and one topic is like it has things related to causality, what consistency checks you can do, about de-embedding, okay, what are the fixtures and all of that, reciprocity, passivity, and all. So this is a real good document that one can have a real look at. And uh, so when I was going to show about how the setup was done, typically when I'll fabricate these boards and do it, I'll have these ports connected. Okay, so usually there is something called as de-embedding. And maybe Robert, I think if you have a video on de-embedding, put that link. If not, you should really do a video on de-embedding as well. Okay, this is a good topic for folks to learn. uh, in de-embedding, what one would do is we will have this we now have this structure where we'll do the measurement, and we will have effects of connector and the cable and all of those fixture effects as well. Okay, but then we will also what we are interested is in this device under test, we call DUT. So this is the only section that we are interested in. We don't want these effects of this port. So there are multiple de-embedding methodologies. A typical one would be they will combine this section together and do a separate measurement of that, and then they'll do mathematical removal. Okay, so we have this one data, and then if we have a sum of these two data and we subtract that, we will get the residual. Okay, I'm explaining it in a very simple way. uh, one can go through some technical details or go through this P370 document to understand. So
Well, I will interrupt you because I have good example on this. So uh, if I would like to explain that this kind of method is, for example, used when memories are measured. Because when we measure memories, We have to put there something what is called
Interposer.
interposer. Yeah. So we can probe the oscilloscope, for example, on our signals, DDR signals under the memory chip. And then what we can do in the oscilloscope, we can take the S2 parameters models of this interposer, and we can do this de-embedding, and mathematically we can actually see the signals which would be measured directly on the pins of the memory. Even we are not measuring directly on the pins of the memory, we are measuring on the interposer. Correct? That's okay.
Yeah, yeah, yeah. Done. Yeah. So yeah, so this I wanted to stress the importance of de-embedding, and you mentioned a good example, and even now the latest thing would be HBM. Okay, the HBM memories, they are getting stacked on one on top of one another. So measurement challenges for that is a case. So you'll see more and more about de-embedding your interposers in the new things that would be coming up. So what I had here was, I don't have connectors in the example that I showed you. So I was first going to make it very explicit that, hey, I don't have this text fixtures. I have not done de-embedding and all of that. So all the results that you will see, you'll see the profile of the ports effect. You'll also see that impedance, whatever we are going to discuss. And I had this as an initial slides basically, but this is the
Yeah,
important yet boring stuff, or unknown stuff.
I understand.
But
Yeah.
the other case that I had was about this gap in a return plane. So we have a cutout. Okay, so usually the return plane has to be a solid plane basically with no gaps. But sometimes when you're routing, you may have some jump overs. Okay, so if you see a TDR profile again, if you are biased towards TDR profile and you just go and see that, you will see this discontinuity. Okay, um, the red curve is the no gap. So you see that there is a port in the previous slide I showed you. There is a port one and there is a port two. At both ends we have this port. But when you see the gap, the response TDR response of gap in the return plane, you don't see this effect. Okay,
Mm-hmm.
where did that did the port 2 got vanished? Like, that would be a question, right? So this is also where we should do some consistency check. Okay, so this is another good habit that one should get into, and that is switch the ports. Okay, so the blue curve that I have here is TDR response from seeing it from port 1. Okay, and then I'm just uh, switching the S parameter and now seeing it from port 2, and you see it exactly overlay. So you see that you are not seeing this port out here is because of the resolution, and that's what I had shown you previously as well, that
Mm-hmm.
you need enough rise time and all of that. So this is an artifact that just got smeared with, because that when by the time this was coming up, it hit the open, so it did not get a time to go down and come back.
Mm-hmm.
It simply just went to the open. Basically, that signal, when it was traveling, it was just in the rush basically.
This is
Okay,
interesting. So
let's
it means when you do this TDR analysis, you need to know what you are doing. Otherwise, you will see something
yes.
what is not really true.
Yes, and that's where using those rule of thumbs, those consistency checks, using that rule number 9. Hey, what do you anticipate? So initially you anticipated that you should see a via, but you are not seeing that via. So why would you not see a via? Is that like no? It's not via. Sorry, it's port. My bad. Okay, the via signature is also same, so that's why I by default said it via. Uh, so this is port. You did not see that port. So why? What was there? So you can just invert it and see it from the other side, and you will still see that port. So that means there's no issue with your model. Your model quality is good. It's just how how this transition is happening from where it is recovering from that and just simply going to an open
So
basically.
if you would rise the rise time, then or if you would speed up the rise time, then you would see it.
Yes, then you would see it, but then for that you will have to do a EM extraction up to higher frequency, or a measurement up to higher frequency, because that is a relation, right? Bandwidth and rise time. Yeah.
And it takes
But
longer.
Yeah, it would then take longer and all of that. Yeah. And other thing that I wanted to stress from this slide is you see that gap, okay? And if you simply just get this data and connect TX, RX, and CI, you will still see this may pass any eye mask response basically. So you may assume that, hey, my design is good. uh, so you need to switch your views. Okay, few things you will get a good visibility from time domain, few things you will get good visibility from frequency domain. So you need to build muscle around just switching things from time domain to frequency domain. That will help one get a better intuition and a better understanding of things.
So how does
And
it look in frequency domain? Do you have
uh,
pictures?
uh, no, I I don't have a frequency response picture of this, but what other thing that I want to see show is when you see there is this reflections happening because of this ground, the gap basically, but that they are not of a very high magnitude. So you just see there is some additional noise getting added onto the V high and V low values, but it's not impacting enough that it is collapsing
Mm-hmm.
the eye completely basically. And also if you see the difference, this is like 87, and where it is coming right now is around 74 kind of thing. So it's also not a great difference like the way we saw it in
Mm-hmm.
previous example, right, where it had meanders. From 80 it went all the way up to 120 plus kind of thing. So that was a very large difference. This wasn't that large of an impedance difference. That's why you don't see much reflections. So what what is that ballpark region, or why you are like this will help you build intuitions and understanding as you go forward basically. Yeah. So this
Okay.
was it, and then the main slide that I can bring up to is this one. Okay, so the few images that I showed and all of that was from Eric's book. Okay, and this is that chapter 15. Okay, there is nothing as differential mode or common mode. Okay, even though we were using mode conversion. Okay, but let's say that, hey, there is differential signaling, differential impedance, common signaling, common impedance. And you would see when I was talking, I was also reminding myself again and again, common signaling, differential signaling. Because the more you start using this language, it becomes easier. And right after this image in his book, he have got around 10-15 statements on how you will be communicating this. Okay, just two examples is, hey, a differential impedance is an instantaneous impedance that a differential signal would see propagating down the differential pair. Okay, the common impedance is an instantaneous impedance a common signal sees when it's propagating down a differential pair. So this is how, like, he has got this 10-15 statements right after this image on in chapter 15, that one can get a hang of basically. So this was something that I wanted to
Uh,
show basically.
go back. So if someone is interested, actually we did a video with Eric about differential pairs. So if someone is interested, they can watch this video. Again, it was really, really good, and it was the main idea behind the video was like, so is there like ground for differential pairs or not? That
Yeah.
was the main idea. Like,
Yeah, and the thing is, yeah, he had increased the separation of that. That was the work that I had done back when I was a student at CU. Like, so the image that he shows is the same work that I have done. Yeah,
okay, so what else do
yeah,
you have here? So if
yeah.
someone would like to
That's
understand a little bit more about differential pairs, watch this video. Again, I will put somewhere
yeah,
information about the video.
yeah. That's broadly what I had. I don't think I have anything else. Basically, yeah.
Okay,
I assume I have covered all the takeaways that I wanted to cover. Yeah, the one key thing is definitely build understanding around both things, frequency domain and time domain analysis.
yeah, and I would like to point out this because I remember. So I started with the time domain because of the oscilloscope and all these things. But then I found out even if you measure everything looks correct in your scope, the problem is you see the results on your scope only for this specific signal running at this specific frequency. And if, for example, frequency of your signal will change or something like this will change, you don't see this result. It doesn't mean the signal will still be same and same quality. That's why we would like to also see the frequency domain or frequency characteristic of this PCB, for example, because then we can very nicely see that, for example, for specific frequencies, there can be problems because there will be the drop. And if our signals are running at these frequencies, then it may be wrong. And that's why it's important to see time domain and also the frequency domain.
Yeah, I can relate because I came from RF background. So I used to naturally think in frequency domain first and ignore time domain. So I was struggling a lot initially to build muscle around time domain analysis, but it comes handy. So something that you don't see in time domain, you see in frequency and vice versa.
Yeah. Okay, so what in the next base techno methodology, cutout, okay, length mismatch, we did this, crosstalk, okay, we did this.
Yeah.
So that's it?
Yeah, that's it. That's it from my end.
Thank you so much, Saish, because it was a lot of work to prepare these examples, so thank you very much for preparing them. You specially prepared them for this video. Thank you.
Yeah, it was fun. Like and trust me, this last example about how this sequence of P and N happens at differential to differential, that was a curious case that I got to work with. So thanks for that opportunity, basically. And I am going to build a board and do a measurement. So maybe I'll send you the data or slides when I complete that. Maybe let's see.
Okay. Thank you so much.
Thank you.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEvel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.